vibrate plates and to measure energetic radiation. So why would we do that, and what does it have to do with this conference? So there's really two motivating factors. One is a number of experiments that showed anomalies, more specifically mechanical vibrations associated with X-ray and neutron emission. And then there is Peter's theory development, which in fact suggests exactly that kind of effect. And the theory development, it's interesting, the theory development was motivated originally by trying to account for the absence of energetic radiation in the Fleischmann-Ponz type of experiments. And so here you see the connection between those 2 points. So here you have energetic radiation where you wouldn't expect it. And here you have the absence of energetic radiation where you would expect it. And so I don't have much time to walk through these experiments, but the most important ones are the Karput experiment and the Konilova and Wysotsky experiment. And what you need to know about those is that in both of those you have vibrating steel, very likely with mercury contamination on the surface, that produces 1.5 keV collimated X-rays. And here are the references, and talk to me after the talk if you want to find out more about this. So Peter's, I can only walk through this very quickly. Peter will talk more about his model later. But basically we start with a very much of a textbook approach. We start with a many-particle Dirac model for the nucleus. So you see here we're summing up overall the nucleons, and we have kinetic terms and a nuclear potential term. And to get another layer of detail here, we are splitting up the absolute momentum of the nucleons into center of mass motion and into relative motion of the nucleons. And then what's typically done to get the non-relativistic limit of such a Hamiltonian is you apply a Foddy-Watt-Heusen transformation. And Peter has done that in a way where he hasn't completely moved to a non-relativistic Hamiltonian, but the intuition here is that the center of mass motion, so the motion of the nuclei in the lattice, it does not get anywhere close to the speed of light, so you want to keep that, you want to treat that non-relativistically, but the relative momenta of the nucleons you want to keep treating relativistically. So this is what the Dirac model looks like after applying this transformation, and just want to take a moment to look at it in more detail. So we have the kinetic terms up here.